Hello everyone, it's Dr. C. Hope you're doing well. It is April 10th and it is snowing in Flagstaff, go figure. Not a whole lot of snow, but pretty exciting, I guess. All right, so this is going to take the place of Thursday's lecture. I will try to keep it obviously shorter than an hour and 15-minute lecture, but we do have quite a bit of material to cover. So what we're going to start with here is we're going to wrap up strong acid, strong base titrations. We'll talk a little bit about weak acid, strong base, and weak base, strong acid. We'll do a couple of problems. And then we will get started on precipitation reactions and solubility equilibrium. Okay? And we'll kind of tie this back together on Tuesday when we have class next week. All right. So we spent quite a bit of time on strong acid, strong base titrations. These reactions do go to completion. Okay, so it makes our life easy because it's easy to do the calculations. If you were not in class on Tuesday, make sure you get the notes from somebody and all the calculations that we did in class. Okay, the equivalence point obviously is a very important point of the titration. Probably the most important point. The point where you've added just enough base to completely react with the acid. Okay. So hydroxide from the base reacts with H plus from the acid. So here is the real reaction to produce water. Okay, so for every one hydroxide, you need one H plus, okay, to produce one water molecule. So this would be a strong acid, strong base. Okay, the other product which we talked about in class was the salt that's produced. Turns out that salt is a neutral salt, so it is important that you do know salt solutions for the exam and just know them in general. This salt contains the conjugate base of a strong acid, which has no base strength in water. So the pH is 7 at the equivalence point for a strong acid, strong base titration. Okay, remember alkali metal cations are not going to affect the pH, and chloride is the conjugate base of a strong acid. The stronger the acid, the weaker the conjugate base. And chloride is so weak as a base, it's a weaker base in water. It does not function as a base in water. Okay? So we kind of covered a lot of that in class yesterday. I always keep this picture because when, I don't know if it was as a undergrad or grad student, I used a pH meter very similar to this one, which had a red LED display. You don't see that anymore, so I thought that was kind of interesting. The other thing you'll notice is that this has an indicator here that you should be very familiar with. That has phenolphthalein in it. You can see that light pink color of phenolphthalein. All right. So you do need to know for the exam, and you should know in general, these shapes of titration curves. Okay. Strong acid, strong base titration curve. We did calculations in class on Tuesday, and we noticed that for quite a long way into the titration, the pH didn't change very much at all. Okay, and then of course when we get close to the equivalence point, it's going to shoot up very quickly. Note the pH at the equivalence point, pH equal to 7, and then obviously once we get past the equivalence point, we'll have excess base. So this would be starting with strong acid, adding strong base to that. Now we could go the other way. We could start with strong base in the flask and then add strong acid, and our curve would be opposite. We'd start at a high pH, and then the curve would look like this. Okay? So make sure you know that we don't have to start with acid and add base. We could start with base and add acid. All right. There's an error in this slide. This should say strong acid, strong base titration. And the point of this slide deals with choosing an appropriate indicator. Now, strong acid, strong base, this region of the curve is so steep that our choice of indicator is not as crucial as it's going to be for a weak acid, strong base, or a weak base, strong acid. And we're going to get to that in a minute. Okay? So, yes, we do want one theoretically that changes at pH equal to 7. Okay? But probably up here at pH, starting at about pH 8 or so for phenolphthalein, that's maybe one extra drop, maybe only a half a drop. We're going to be really close. Methyl red's going to start changing not too much past pH 4. Okay, that might be 1 drop less or a half a drop less than pH 7. So the point is, yes, we would, if we were using an indicator rather than a pH meter, we would want an indicator that changes about pH 7, but pH 8, pH somewhere a little less, we're going to be really close anyway. All right, and we'll talk in a little bit about the pH range for when an indicator changes color. Now, weak acid, strong base, the pH is not 7 at the equivalence point. Okay, pH, so keep this in mind. This is only for a strong acid, strong base that it equals to 7. For weak acid, strong base, or weak base, strong acid, it is not 7. So let's look at what we get. Well, it's the same reaction. The main reaction is H plus from the acid combines with hydroxide from the base to produce water. That is the reaction. 1 H plus, 1 OH minus, 1 water. Okay, but because our acid contains an anion, the conjugate base of that acid, and our base contains a metal cation, we also get a salt that is produced. Now, as we've talked about, potassium ion, alkali metal cations do not affect the pH. But acetate, CH3COO- is the conjugate base of acetic acid. And what kind of acid is acetic acid? Yeah, it's a carboxylic acid, so this is a weak acid, which makes acetate what? Yeah, it makes that a weak base. Okay, so at the equivalence point, we've added just the right amount of base to completely react with the acid. So all we have is a salt solution at the equivalence point. Okay, that's all we have. So we have potassium ion, that's not going to do anything. We have water, yeah, these are aqueous solutions, there's lots of water. The key component at the equivalence point that's going to affect the pH is acetate. It's the conjugate base of a weak acid, and that is a weak base, so the pH will be, and this is just in general, I'm not asking for a number, is it less than 7, equal to 7, or greater than 7? Yeah, this is a weak base. pH will be greater than 7 at the equivalence point. Okay, so you need to know why. So weak, you can memorize it, weak acid, strong base, pH is greater than 7. And a lot of students remember that because they think, oh, it's strong base, so it's got to be greater than 7. But it's actually not the strong base that determines the pH. It's this weak base, it's the conjugate base of the weak acid. So you need to know why. All right, so let's look at a titration curve here. And you actually did titrate an unknown weak acid in the Chem 152 lab. So you've seen titration curves like this. And I'm not going to spend very much time here, but you do see a little bit of difference. We're going to start at a higher pH because it's a weak acid. And then this region of the curve is called the buffer region, because you have both the weak acid, let's call that HA, and the conjugate base in solution together. And you probably didn't know why at the halfway point, so the halfway point would be about 12.5 milliliters, which is somewhere in here, right? That pH is equal to pKa. You did that in the lab and you were just kind of told, okay, pH is equal to pKa there. Well, that's because at that point, the acid and its conjugate base are equal. That's a buffer. Those are equal in concentration. And when they're equal, what's the pH of the buffer? pH is equal to pKa. Ding, 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 ding. Okay? Now, other key point, equivalence point. Look at the pH. It's kind of close to 9. So we're not going to do a calculation here to figure out the pH. We could, because essentially we just have a salt solution, and you know how to determine the pH of a salt solution, right? But typical weak acid, strong base, pH is somewhere around 9. That's typically what you see. This one happens to be 8.72. Okay, but it's somewhere around 9. It's greater than 7. Okay, so make sure you know that. Make sure you know what species in solution is making that pH greater than 7. What is it? It's the conjugate base of that weak acid that makes the pH greater than 7. All right, let's talk about the other situation, then we'll do a few problems. Weak base, strong acid. So here is our most common weak base, ammonia. It is an amine. You should know why that's a weak base. And there's our strong acid, HCl. Reaction, H+, it's the same thing. H+ from the acid is gained by the base. We end up producing NH4 plus, ammonium, and chloride. This is our salt. Okay? At the equivalence point, you've added just the right amount of acid to completely react with that base. So again, at the equivalence point, all we have is a salt solution. Okay, acid is gone, base is gone. This salt solution contains NH4 plus and Cl minus. We've already talked about chloride, conjugate base of a strong acid. That has no base strength in water. Don't worry about that. But what about NH4 plus? Yeah, that's the conjugate acid of a weak base. Ammonia is a weak base. So what does that make ammonium in water? Yeah, ammonium is a weak acid. So pH, neutral, greater than 7, less than 7. Obviously, this is an acid. pH is less than 7 at the equivalence point. Let's look at a titration curve. I'm sorry. A lot of stuff, wind blowing today, a lot of stuff in the air. All right, so here's our weak base. High pH, although not as high as a strong base, up about pH 11. We're going to have that same buffer region in there. The pH here would also be the pKa value at the halfway point. OneNote. Okay, well, OneNote stopped working on me. Let's try that again. All right. So again, halfway point, pH is equal to pKa. You know that. Look at your equivalence point. Typical weak base strong acid, pH will be approximately 5. This one happened to be 5.28. All right. And you will notice, and we're going to do, I think, one more slide here to talk about indicators. Your choice of indicator for a weak strong titration, let's just call it that, is going to be more important. Okay. Oh, and I don't have a pH slide there. We'll come back and talk. This actually relates to blood buffers. We'll do that in class. So let's talk a little bit about indicators. This region of a weak strong titration, in this case a weak base strong acid, it's not as broad as a strong acid strong base. So you have to be more careful in your choice of indicator. Okay. Now, when does an indicator change color? Well, an indicator, and let's just do this very quickly, contains both an acid and its conjugate base. So here's our acid, a weak acid. It's actually a weak acid. And its conjugate base, which is a weak base. Okay, so it has both components present. It's, in a sense, although we're not adding very much indicator, technically is a buffer, or becomes a buffer when you have both components present. But let me say that again. It's really not a buffer, but depending on the pH, the two components can be present. Okay, so that's probably a better way to say it. The cool thing about an indicator is the acid part of the indicator has a certain color, and the base part of the indicator has a different color. Okay, so typically when the solution is acidic, you'll have the acid color, and when it becomes basic, you'll have the base color. Now, it will depend on the strength of the acid compared to the strength of the base. Now, let's take the reason why I indicated buffer, and I was ahead of myself. If we do think about a buffer where we have these two components equal, what is the pH of that buffer if the acid and base component of the buffer are equal? Yeah, pH is equal to pKa. So a buffer, gosh, that's a buffer. I'm having trouble already today. An indicator changes color centered on its pKa value, because that's when you're going to have equal amounts of the two colors. Okay, you're going to have equal amounts of the acid color and equal amounts of the base color. Now you might remember for a buffer, we talked about the effective buffer range being plus or minus 1 pH unit. It's kind of the same for an acid-base indicator, because when you only have 10% of, say, the base component, you're probably going to start seeing that color. Conversely, when you only have 10% of the acid component, you will still see that color. So typical indicator, I almost said buffer, I've got buffer on the brain. Typical indicator is going to change over a range, pKa plus or minus 1 approximately. So let's go back. I thought I had a slide with some indicators on it, but I do not. Let's go back to our strong acid, strong base. So phenolphthalein has a pKa value that's about 9, but it's going to change over a range because of having different amounts of each component of that indicator, the acid and the base. So this would typically change from about pH 8 to 10, okay? Because the acid component is colorless. When we get to about pH 8, we're going to have about 10% of the base component, which is this pink color, and we're going to start to see it. Okay, methyl red, as you can see, changes from about pH 4 to 6, which would mean its pKa value is about a 5. So that's why we have different indicators. It depends on the strength of the acid part of that indicator, which has one color, compared to the strength of the base part of that indicator, which has a different color. All right, I didn't do a great job there, but hopefully that got the point across. All right, I think that's what all we want to do with titrations, other than let's do some calculations. So you should have this handout from class. Here's the first side that we did all this strong acid, strong base titration stuff. If you were not there, get that from somebody who was in class on Tuesday. Let's get to problem 2. You should recognize this problem. This was experiment 6 in the Chem 151 lab last semester. Okay, so let's look at what we have. We have a base. And this might not look like an acid, but it does have an acidic proton. And this is an acid that's called potassium hydrogen phthalate. Now, for our purposes, we're going to abbreviate this KHP for the rest of this problem, rather than having to write out that whole formula. Some people don't like abbreviating KHP because P makes it look like there's phosphorus in there, but the P stands for phthalate. Potassium, K, hydrogen, H, P for phthalate. Okay. Now, this is an acid-base reaction. We are titrating that acid with the strong base sodium hydroxide. Now, you might remember what you solved for in that experiment. Mass percent KHP. So to solve for that, we need the mass of KHP, the part, divided by the whole, which is the sample mass, multiply by 100 to get a percent. So this unknown that you had in the 151 lab contains some KHP, but it also contained, let's say, what we'll call an inert ingredient that does not react with the strong base. Okay, it's technically not an inert ingredient, but it doesn't react with strong base. So it's a mixture, and you want to find out what percentage of that mixture is KHP. All right, so look at what we have. 0.542 grams of the unknown. Now you weighed that out in the lab, it's given here, but that is the sample mass, and that is given. So to get the mass percent, what else do we need? Yeah, we need to find the mass of KHP in that sample. And how are we going to do that? By titration. So we titrate it with sodium hydroxide, 0.106 molar. It takes 19.45 milliliters to reach the endpoint. We would probably use phenolphthalein as an indicator here because this is a weak acid. So the pH is going to change about 9. That's a that would be a good choice. Phenolphthalein would be a good choice. Changes around pH 8 to 9 in there. All right, so molarity in liters. This is a stoichiometry problem. Molarity times liters gives us moles of NaOH. Okay, so molarity, 0.106 moles per liter times 0.01945 liters. .00206 moles NaOH. But that's not what we want. We want KHP. Stoichiometry. That's not hard, right? And this is nice. 1 to 1 mole ratio. 1 mole KHP to 1 mole sodium hydroxide. So that just gives us that same 0.00206 moles KHP. Not so bad, huh? Well, we don't want moles, we want what? Yeah, we want mass. How do you go from moles to grams? Molar mass. Calculate this out. Potassium, 5 hydrogens, 8 carbons, 4 oxygens. You should find about 204.22, so we take that 0.00206 moles of KHP times 204.22 grams per 1 mole. KHP, moles cancel, we're left with grams, and you should find about 0.421 grams of KHP. Are we done? Almost. Almost. That is now the mass of KHP in our sample. It should be less than our sample mass, which it is, because that sample was a mixture. So mass percent, I've been trying to get a different pen color here, and it's just not helping me here. There we go. Mass percent, part divided by the whole, the part that is KHP, divided by the whole mass, which is the sample mass, multiply by 100 to get a percentage, and you should get about 80.4%. I think it's about 80.35%, and that is choice C in our choices up there. Okay, so for the strong acid, strong base titration, we calculate the pH at various points along the way. We did that Tuesday in class. But remember, the most important point of the titration is the equivalence point. So from that point, we could get mass percent as we did here. Another common calculation is molar mass, and I think you'll see that in some of the practice exams. Maybe we'll do one of those in class on Tuesday. Determine the molar mass of an unknown acid or base from a titration. Okay, and so it essentially becomes a stoichiometry problem. Molarity times liters gives you moles. You can then apply the mole ratio to get the moles of what you need. In this case, we need grams, not moles, but you get the idea. Stoichiometry. All right, a couple more that should be pretty quick here. We already talked about these. pH at the equivalence point for a weak acid with a strong base. What is it? Yeah, it's greater than 7, because that weak acid, when that reacts with the strong base hydroxide, we are going to produce the conjugate base of that weak acid, which is a base. The conjugate base of a weak acid is a base. We also get water, okay, but these are all aqueous. There's tons of water. So the key product that's going to determine the pH at the equivalence point is that conjugate base of that weak acid. It is a base, pH greater than 7. All right. Indicator question. We've kind of talked about indicators. I didn't do the best job there. But what is ammonia? Weak base. HCl. Strong acid. Now you'll probably memorize this, that the pH is less than 7 at the equivalence point. typical pH is about 5 for your typical weak base strong acid. Okay, so you want an indicator that changes about 5, okay, which would be choice A. Okay, so that would be the best choice. Now, also make sure you know why the pH is less than 7. What species in solution is making that solution acidic, pH less than 7? And again, it's the conjugate, in this case, conjugate acid that is produced. H plus from the acid is gained by the base to produce the conjugate acid. This is the conjugate acid of a weak base. That is a weak acid. And the pH will be acidic, less than 7. Okay? So, yes, you can memorize things. It's better to understand it and know what it is that determines the pH. Also keep in mind at the equivalence point, you've added just the right amount of acid to completely react with the base. So those are not present in solution. All you have at the equivalence point is a salt solution. And in this case, it's the ammonium ion, the conjugate acid of that weak base, that determines the pH, pH less than 7. Okay, so I've gone for not quite a half hour. Let's transition to the last topic of this chapter, and that is precipitation reactions. Now, I think it was the 151 lab. I don't think you've really done precipitation reactions in 152 lab. You did a bunch of these last semester. And they're pretty cool. I just think that you take these two clear solutions, you mix them together, and this solid just, boom, comes out a solution. Okay. Now, unfortunately, in the old days, you used to get better colors because there are a lot of really cool colored precipitates. Unfortunately, those tend to be toxic or are really strong oxidizing agents and whatnot. So those have kind of disappeared from the general chemistry lab over the years. But I think you did silver chloride, nice white precipitate. Okay. Now, equilibrium hasn't gone away yet, but we are getting closer to wrapping up equilibrium, and we will do some new material here pretty soon. So you probably remember the solubility chart from last semester, and we kind of just classified things as soluble or insoluble. So when we classify something as insoluble, it doesn't mean that it's totally insoluble. Okay? A little bit will dissolve. And so you may remember, you may not, sulfides tend to be insoluble. Sulfides. Okay, so if you look up in the solubility tables, sulfide salts tend to be insoluble. So copper sulfide is insoluble. But a little bit of that salt does dissolve. So remember, when we dissolve a salt, we break it up into its component ions. For a soluble salt, we put an arrow, single-headed, saying that goes 100%. For an insoluble salt, it doesn't go very far at all to product. We don't get very many ions in solution. Now, you might be asking, where's the water? A lot of times we just write water above the arrows because water is not technically reacting with the salt. It's just hydrating the salt and pulling some of those ions into solution. Okay. Now, this is an equilibrium. This is actually an equilibrium that lies far to the left, so our K value is really small. And we give it a special name, KSP. This stands for solubility product. So the solubility, when we write this out, it's just going to be the products of our reaction. We'll see in a minute. For this reaction, it's going to be quite small. Now let's write it out. Well, we have a pure solid and a pure liquid on the reactant side. Those aren't in there. So it's just the products, the product ions. Copper 2 plus, raise the power of the coefficient, which is a 1. Sulfide, raise the power of the coefficient, which is 1. So of all the equilibrium problems we've done so far, I think these are the easiest because the only thing that goes into the expression are the product ions. That's it. Now, where students get confused, we describe these as precipitation reactions, but the way we set these up and what the K values are for is for that salt dissolving. Now, it doesn't dissolve to any great extent This equilibrium lies very far to the left, and you can see me pushing my hand to the left, right? Left, right? Yeah, okay. This equilibrium lies far to the left, but we do get a little bit of product ions, okay? But that's all that's in our expression. So solubility, just like anything, the smaller the K value, the less it goes to products, hence the less soluble. And the two types of solubility that we're going to consider, most often we'll look at solubility in moles per liter, molar solubility. But solubility is also often expressed in grams per liter. But when we solve these, it's going to be concentration. Just like Kc, Ksp is concentration and molarity. Okay, these are applications. We'll talk about those in class. So look at the new handout that will be posted. And let's do a couple of problems, and then we will call it a day here. All right. So most hydroxides are insoluble. Aluminum hydroxide is not very soluble, but it does dissolve a little bit to its component ions. Aluminum is a 3+ cation. Hydroxide is a -1 ion. Okay, so we get those two product ions. That's all that shows up in our equilibrium expression. That's it. So the correct answer here is not that one. Oh, it's actually none of these. Okay? Tricky, Dr. C. So the correct answer would be aluminum 3+ raised to the power of the coefficient, which is 1. Hydroxide raised to the power of the coefficient, which is 3. That would be the correct expression. All right. Let's see how we do a couple of these equilibrium calculations. And again, we will review these in class on Tuesday. So if you have questions on these, please be prepared to ask questions. Okay? Because I hope you find these easy, but these always can cause some confusion because of the x terms and the exponents and whatnot. And just writing these out. Remember, we're always writing these out, looking at the salt dissolving. And I think what confuses students is we think of insoluble salts. Well, they don't dissolve. Well, that's almost true. They don't dissolve to any great extent, but they do dissolve a little bit. This is going to give us 3 silver ions. Now, if you don't get the charges right, don't worry. You'll still get the problem right as long as you get the coefficient right. Take the coefficient of 1 times the subscript, 3 silver ions. Turns out silver is +1. Okay? The reason why that is because phosphate is -3. Now, remember our salts will just have 1 cation, 1 anion. So don't try to break up phosphate into other things. 1 cation, 1 anion. Now, note your Ksp value. What do you notice about the magnitude? Yeah, it's really, really small, meaning that this equilibrium lies very far to the left. This salt is not going to dissolve to any appreciable extent. If we mixed a solution that contains silver ion and phosphite together, this salt would precipitate, most likely. Okay. Now, ice tables here are going to be pretty easy. That solid's not in our equilibrium expression. We don't need to know what it is. Doesn't matter. Before that, any of that salt dissolves, we'll say those are 0, -x. Sometimes you'll see these written as -s for solubility. I would just stick with x. X is our traditional variable. Now, watch your coefficients. If x of this salt dissolves, we are going to get 3x of the silver ion and x of phosphate. Okay, so we still have to factor in the coefficients. Don't worry about the solid. It's not in the expression. 3x and x. Doesn't that look pretty easy? The only thing that makes that hard is the coefficient. Now, you are going to see that coefficient twice because you will see it as the exponent as well. So, Ksp is products raised to the power of the coefficients. That's it. Our solid and the water aren't there. So our value, 8.89 times 10 to the -17, is equal to 3x cubed times X. Now, I should have probably mentioned this at the start, but X is the amount of that salt that dissolves. That is our molar solubility. Okay? X is the amount of that salt that dissolves into these ions in solution. So that's all we're solving for. Be careful. 3 cubed, 3 times 3 times 3 is 27. X cubed times X, this is 27x to the fourth. So, divide by 27 first, and then take the fourth root. Well, I'll go ahead and write this. X to the fourth is equal. So I'll divide by 27, just to make sure we're all on the same page. Oh, I did not do that right. Try that again. All right, so this is about 3.29 times 10 to the negative 18th. Take the fourth root. Okay, now your calculator probably doesn't have a fourth root, but raise it to the power of 0.25. So that's what I'm going to do on my calculator. And let me get to scientific notation. X is 4.26 times 10 to the negative fifth molar. So that's it. That's the answer. That is the molar solubility. How much of that salt dissolves in moles per liter? And you can see it's pretty small. That's the highest concentration, what we would call a saturated solution. That's the highest concentration at room temperature that we could make, 10 to the negative fifth molar. This is the molar solubility. Okay? We might talk about, I mean, you've probably heard of supersaturated solutions. If we were to heat up the water and add solid, we could get more of this to dissolve. And then if we allowed it to cool slowly, then more of that salt would stay dissolved in solution. Okay? But this would represent what is called a saturated solution, as much as can dissolve at room temperature. Okay? Let's skip 3 for now, and we'll see if I come back to it after the next calculation. But I want to show you this same calculation, but not in pure water. Pure water does not have any silver ion. Pure water does not have any phosphate ion. But if we try to dissolve this salt in a solution that does contain phosphate ion, it is going to affect the solubility. And let's see how it's going to do that. Okay, so it's the same salt, so it's the same reaction. This is the insoluble salt, so that is what we are starting with. That salt, not very soluble in water, but we will get some silver ions. We will get some phosphate ions. Okay, same reaction we looked at above. Okay, now, this is a soluble salt. And the way you know that is a soluble salt, potentially, you might remember that alkaline metal salts are soluble. But the other thing that tells you that it's soluble is look at the concentration. We were able to make a reasonable solution of that. That would indicate that it's soluble. So that salt is going to give us sodium ions, but it's also going to give us phosphate ions. Okay, so the sodium ions aren't important. They are not what we'd call a common ion. What is the common ion is phosphate. Does the name common ion make sense? Yeah, that ion is common to these two salts. So it's common to this equilibrium. Who missed, and you guys never like when I say this, who missed Le Chatelier? Oh gosh, you guys are cringing. I can feel it. So in effect, in pure water, this would be 0. In this salt solution, this sodium phosphate solution, this is not 0. So in effect, we are adding this. We are adding phosphate. Which way will this system shift to establish equilibrium? Yeah, it's going to shift to remove the phosphate. It's going to shift this way, okay? Which means less of that salt is going to dissolve because we're going to the right as the salt dissolving. This actually shifts back to the left, so less of the salt will dissolve. So adding a common ion will decrease solubility. So make sure you know that. And we're going to do a calculation here to prove it. We're going to see how much the solubility decreased. We know what the solubility is in pure water. It's right there, 4.26 times 10 to the negative fifth molar. Let's do this calculation in this solution. Same setup almost. Don't worry about your solid. It's not in the expression. Silver ion is 0 at the start. What is phosphate at the start? Yeah, phosphate is 0.25 molar. That comes from this salt. When this dissolves, it's a 1-to-1 ratio between the salt and phosphate. So if the salt solution is 0.25 molar, phosphate will be the same at 1-to-1 ratio. Okay, so that's our common ion, shifted the equilibrium back to the left. But since I have 0 for my silver, it still has to go a little bit to product. Don't worry about your solid, it's not in there. Not in the equilibrium expression. And there we go. Oh, what did I forget? Thank you. My 3. Don't forget that. If you do that, of course, you will not get the correct answer. So watch the coefficients. You see them twice. We will again see the coefficient here. Silver ion cubed, phosphate to the first power. Now, plugging in, 3x cubed times, now when it was pure water it was just x, but this is 0.25 plus x. Okay? So compare your work, and hopefully you're writing all this down, compare your work on the problem where silver phosphate was dissolved in pure water to this solution. And the only difference is this 0.25. Okay? Now, look at the magnitude of your KSP. What do you notice? Yeah, it's really small. Not much of this salt is going to dissolve. We are going to make the small x approximation. Okay? So we're going to assume that 0.25 plus x is going to stay about 0.25. Okay? So multiply that out. Again, it's 3 cubed. 3 times 3 times 3, which is 27, times 0.25. So that's 6.75 x cubed is equal to 8.89 times 10 to the negative 17th. Divide by 6.75, take the cube root, and that will solve for the molar solubility. So 8.89 times 10 to the negative 17th, divide by 6.75, take the cube root, or raise to the 1/3 power, and I come up with a value of 2.36, and I don't think we have 3 sig figs, or 2.4 times 10 to the negative 6 molar. Okay, so again, this is our molar solubility. Well, did our calculation bear out our prediction? Our prediction that adding a common ion would decrease the solubility. So adding the common ion phosphate shifts this equilibrium back to the left, decreasing the solubility. What was it in pure water? 10 to the negative 5th molar, 4.26 times 10 to the negative 5th. Now we have 2.36 times 10 to the negative 6 molar. Solubility, I can spell, decreased by adding that common ion. Okay? All right, where are we at here? We're at about 45 minutes. This is another common ion, one of the same thing, except this time we're adding silver. Why don't we save that for class just so we can refresh this in our minds on Tuesday? To wrap up for today, let's go back to 3. Now, think back to a lot of the equilibrium problems that we've worked. More often than not, we were given KSP and we solved for X. In this case, for solubility, X is our molar solubility. Okay? Now, if we want to solve for KSP, X must be given. And in this case, it says our solubility is this, and it's in moles per liter. So this is going to be our X value, essentially telling you your molar solubility. So one thing we do need to know is the formula of that salt. Copper. What does that 1 mean? Yeah, it means copper has a +1 charge. Bromine, or bromide, as a charged species, it's a halogen. How many electrons is bromine going to gain to become bromide? Yeah, just 1, so it's going to be -1. +1, -1, that is the correct formula of that salt. So I chose a really easy one for this problem. Watch for ones where the subscripts are not 1, because then you'll have 2x term. So say your subscript was 2, you'd have a 2x term. Or if your subscript was 3, you'd have a 3x term, and so on. Okay, so watch for that. This salt in water is just going to go to copper +1 in solution and bromide -1 in solution. Okay, now you probably could figure this out without setting up an ice table, but since we've kind of gotten used to doing this, in pure water these would be 0. X will dissolve, that's the molar solubility. In this case we get +1x for copper ion and +1x for bromide. And these are just X and X. And so our KSP is just copper. Okay, plug in KSP is equal to X squared. I'm right at the bottom of the page, but you can see this. And they gave us our X value. So this is, I could have done that without punching that in my calculator. 4 times 2 squared is 4, and 10 to the -4th times 2 is 10 to the -8. So there's our KSP value for that salt. Okay, so we can go either direction. More often than not, you're going to be given KSP and you solve for X, which is the molar solubility. But you can go the other way. You can be given X and solve for KSP. Now, one thing I want to point out here, this was a really easy example where our mole ratio was 1 to 1. Let me just scroll down a little bit. And instead of copper 1 bromide, let's do copper 2 bromide. So copper 2 means copper is +2, bromide is -1, so we're going to need 2 bromides. So when this dissolves in water, we're going to get copper 2+ and 2 bromides in solution. So when we set up our ice table, okay, X is still the amount of that salt that dissolves. Copper 2+ is going to be +X because it's a coefficient of 1, but bromide is going to be 2X. Don't worry about the solid. All right, and so our KSP, and this is where you have to be careful, is that you see that coefficient twice. You see it in the X term, and you also see it in the exponent. Okay, now plug in. Okay, so again, coefficient of 2, 2x, exponent of 2. You see it twice. Be careful. Now, 2 squared is 4, x squared times x. This is going to be 4x cubed. Now, similar problem would give you the molar solubility. It would, in effect, give you x. You could solve for KSP. Okay, so watch for that. Watch for those coefficients. It makes it a little bit trickier. Last thing I promised for the lecture, and I think I'm right about 50 minutes. Not so bad, better than an hour and 15. Solubility, we've only worked with molar solubility, but make sure that you are prepared to potentially answer a question where it asks, and I wish I had more room up here. I haven't, in both of these where I have solubility, I don't have room. I guess I could do it here. We got the molar solubility there, 2.36 times 10 to the negative 6. You will see solubility in units of grams per liter. So molar solubility, moles per liter. Solubility is also expressed in grams per liter. Okay? Do you know how to go from moles to grams? I hope so. All right. So if the problem doesn't ask for molar solubility, but solubility in grams per liter, once you get to this point, you need to convert moles to grams, and to do that, you need, as you know, molar mass. So in this case, we'd have to calculate the molar mass of silver phosphate, and then convert that from moles per liter to grams per liter. Whew. All right. That's a lot of stuff. Hopefully you won't be too bored listening to this. And then on Tuesday, please come with any questions that you might have. Let's clear those up. We'll work a few more problems. We'll review a few things. We'll talk about the exam. And then we'll see if we start any new material or not. But we definitely will use a good chunk of Tuesday to make sure that we wrap up this material so everybody's on the same page and that we're ready for the exam on Thursday. Okay? Have a great weekend. Watch for all the stuff that's posted in Blackboard and in Sapling and other places. Everything that you should need to get ready for the exam and homework assignments and all that, that will all be posted. Okay, so watch for all that stuff. I will see you, well, I will have office hours on Monday next week. Okay, so you can come see me on Monday. If I don't see you at office hours, I will see you in class on Tuesday. Take care.